The first one is Metamaterial Mechanisms, and Alexandra here is going to present.
Thanks for the introduction. So, hi, I'm Alex, and let's talk metamaterial mechanisms. Here's one example of such mechanisms. It's a door latch that is printed in one piece. We've implemented an editor for creating metamaterial mechanisms that includes a finite element analysis for preview. So, traditionally, 3D print has been about shape, shape, and shape. So, they were designing the outside of the objects. The next step is to design the inside of the objects. So, for example, to save material use and optimize the strength-to-weight ratio, to move the center of gravity of objects, or to make objects spin. So what these researchers did were to rearrange material on the interior of the object, but to vary one property. So the next step was then to design many degrees of freedom. In mechanical engineering, researchers divided materials into many, many cells to design the deformation of the whole material. Researchers in computer graphics applied this concept to copy traditional materials like felt and print it from plastic, and even with localized elasticity. So this has been referred to as metamaterials, and specifically in this case mechanical metamaterials, which are artificial structures with mechanical properties defined by their structure rather than their composition. So far, metamaterials have been understood as materials, but we want to think of them as machines. So if we look at the door latch example again, so when a user pushes down the handle, it creates a rotation around this axis, which causes these cells in the middle to shear. And these shearing cells then pull in the latch so the door can be opened. Now this is a traditional door latch that you might know. So again, if the user pushes down the handle, in this case the axle turns, which charges the handle spring that is behind it, and at the same time the lever is moved, which in return pulls in the latch, and that again charges the latch spring, so the whole thing comes out again when you release. So as you see, there are quite some parts involved here that need to be assembled. So in our case, we print this whole mechanical device that is functional from one part. So obviously it requires no assembly. Then furthermore, we organize everything on a standardized grid, which allows us to reuse specific components, as you will see throughout this talk. So I want to show you the elements of metamaterial mechanisms at hand of this, at the example of these simple pliers here. So they work like this. And here you see the grid I was mentioning earlier. So all this, the whole object is subdivided into into cells of a regular grid, and each cell looks like this. So it's just a square with two diagonals, and we can pick any beam we want from there. So you see this one cell here. That is a rigid cell. It has a diagonal, so it won't move. And that enables us to kind of model the material and make like rigid areas, which we like to call members. In contrast to the rigid cell, you see the shearing cell that allows for a controlled directional movement. So the shearing cell has no diagonal, so it has more degrees of freedom it can shear. And if we assemble more of these together, then we like to call this the hinge array. Now let's dive a little bit deeper into this topic of hinges. So the most naive approach would be to just take the cells and then you make a very thin connection so it actually deforms. And this is inspired by so-called living hinges. It's like making the material very thin so it flexes, it's one part, it's all great. And this is kind of the metamaterial rendition, if you so will. However, this approach would generate a really weak hinge there. So we set out and replicate multiple of these hinges here, and that allows our hinges to take more force. And again, this is what we refer to as the hinge array. Now you see how it deforms and they all shear in a very controlled way. So the rotation is fine, that's cool. But then at translation, if you pull it apart, it still breaks. So why is that? And that is because all these additional hinges that we added, all these shearing cells, they still act independently on translation especially. So they don't really take up more force than they did before, like this one hinge in the middle. So we make sure that they actually act as one big thing, and add additional cells on the outside. So what we've seen so far were hinges. So that's the it's kind of the hinges located between adjacent members. Now, if we look at opposing members of a hinge array, then this actually implements our metamaterial rendition of a 4-bar. So here you see the 4-bar individually. You see that the opposing members always remain parallel to each other. And this is essentially what implements our pliers. So what I showed you so far were the hinge array and the 4-bar, and we call these basic mechanisms. Now, if we concatenate 2 or more mechanisms, then that's compound mechanisms, and we use that in the example of our pantograph, where we concatenate multiple hinge arrays. So the pantograph just redraws whatever the user draws on the one end. It essentially just copies the drawing. Okay, so now you've seen the basic shear cells, which are actually the key idea of implementing these mechanisms. But we have a couple of more variations. So in this, here are the legs of the Jansen walker. It's also very known under the term strand beast. And here we have the regular hinge array, which we just saw, and that just shears on the vertical beam trajectory. Now, if in this case we want to allow for different types of for a different type of movement, so we have what we call the rotated shear cell, and this is actually so it's a shear cell that is rotated by 45 degrees, and it's compounded out of 4 cells where only the diagonals are still present. So another type of cell that we kind of have in our repertoire, we call that the preshared cell. And it's similar to the regular shear cell, but it travels on a larger trajectory, namely on the diagonal. Now, we use them, for example, for padding. So let me explain what we mean by padding. This is kind of a very early version of our door latch. It's still fully functional. As you see, it's anchored down there because everything else is moving. And while it still performs the function we want it to, it's not very stable because you can just push it out of plane. So here's the new door latch, and these are the padding cells. So we use that larger movement of these cells to make the mechanism more stable, to prevent pushing it out of plane, and they're only there to kind of absorb the movement and enable us to embed the mechanism into kind of a rigid material, walls, a door. Now, and this yields kind of the hierarchy of metamaterial mechanisms. So on the lowest level, we have cells, and they perform an elementary function of elementary mechanical function, like, for example, the shear cells or the Z cells, preshared cells. Then one up, we have the compound cells, which also perform an elementary function, but they are implemented using multiple cells, like the rotated shear cell. So from these cells, we can create a basic mechanism, usually by repeating the cells, like the hinge array or the four-bar. And then on top of that, we can concatenate these basic mechanisms into making compound mechanisms. And on the highest level, we kind of see the machines, so they perform a mechanical function. They consist of one or more basic mechanism or compound mechanism. Now, to help users design such metamaterial mechanisms, we implemented a voxel-style editor. This is very suitable because our materials are organized on a grid anyways, and then we have the voxels that are also regular units. So our editor allows for editing metamaterials, like in this example here, where a user just lays down the kind of the bulk material of the door latch first, and then uses the shear cell brush to allow the material to deform. Now, to actually check before printing or fabricating in any other way if it works, we also implemented or integrated a finite element analysis, where the user specifies where the object is anchored, and then applies a force by dragging the handle downwards. So what I showed you was shearing in one plane usually, but here is a simple example where we show that we can, so our editor also supports shooting, like making these shear cells in multiple directions, and in this case we have two shearing areas where the green one shears on the, excuse me, the green one shears on the XZ plane, and the blue area shears on the XY plane, so that the latch can latch under this hook. So our editor is implemented in WebGL, using WebGL and 3JS. The finite element analysis, for that we use Karamba, which is a plugin for Grasshopper. So we send the mesh data and the anchor points and the force to Karamba and get the transformed vertices back. Then when you're done, you can export the structure. So we use OpenJSCAD to export, like to generate all the beams and all these little structures in there, and render it back to you in an STL file. So we also set out to see, to learn about the durability of the materials and also of the structures. So we printed, for example, these pliers in first in NinjaFlex, which is a popular rubbery filament to buy, then also in SemiFlex, which is a little bit stiffer than NinjaFlex, PLA, which is the commonly known, one of the very common filaments, and it's rather stiff and weak. And my favorite one that I just kind of discovered is nylon, because it is as stiff as, it feels as stiff as PLA, but it's much stronger. So the higher level message here is that our structures work throughout different materials. However, material and geometry always interacts. So the weaker the base material, I would say, the larger the cells should be, because then the bending radius is not getting too small. So next, to see how durable the mechanisms are, we hooked up our Jansen walker to a power drill and operated it like 5,000 times, and we could not find any fractures or failures. So what you didn't see so far is that actually these little structures, they also have a thicker area they're thicker in the middle, which increases the member stiffness, and they're thinner at their ends, so it decreases the hinge stiffness. So, and this is to have the deformation, but still be rigid enough to transport force to the neighbor cell. So in our prototypes, because we were printing them on consumer and 3D printer, the Ultimaker, we used just a thickness ratio of 2:1, so that gives you a stiffness ratio of 8:1. So that also means that the members deform during use, which is not desired, but. And this again limits how many basic mechanisms we can concatenate. And this again limits the complexity of the machines. So if you could have a thickness ratio of 4:1, for example, it would give you a stiffness ratio of 64:1. So you could use, for example, high-resolution printers, or also multi-material printers would be a way to go. And this would allow for more complex machines. Another limitation is that since everything is based on deformation, we cannot have continuous rotation like axles and stuff. And you saw in the Jansen walker we added the axle. And to conclude my talk, I presented metamaterial mechanisms, which have the benefit that they implement mechanisms or machines into one single part, so there's no need for assembly. We also showed a 3D editor to create these machines. However, as mechanics you need to have some knowledge there, so it is still an expert tool. But we think that our main contribution is that we don't consider metamaterials as materials anymore, but we think of them as machines. And this actually, so the main promise of this works is that it allows us to achieve a deeper integration between the structural and the mechanical functions of materials. So last, I want to thank all my co-authors, where 2 of them are here. Can you please wave? Thank you. And I'm happy to take questions.
Okay, we have time for at least a couple of questions.
Hi, Florian
Hi.
Paterneder, Media Interaction Lab. I was wondering if there would be the possibility to give some guidance to the user when designing those machines. I mean, you mentioned it's an expert tool, but if I know kind of the force I want to apply, well, what cells do I use?
Yeah, so that's actually something that that we're working on right now. So this project was also an exploration of the structures themselves, and everything that we learned during this project, that's kind of the next step to build that into software and give users hints when they make hinges that won't move, for example, because there's still some rigid material, or also to let to have like a higher level kind of way to edit where you're not on the cell level but have like more the compounds. So yeah, definitely that's something that we want to do next.
This is really nice stuff. So you've made these machines that are designed to be made out of either a single material or potentially multiple materials used together. But in each case, each material has properties that are essentially constant. And I was wondering if you thought about taking into account how they might behave differently if, for example, you change temperature to maybe build things that you could temporarily heat parts up or cool parts down to make them react differently.
That's a really cool idea, yeah. It would actually be a way to kind of have actuated materials. So, to be honest, we didn't talk about it yet, but I think it's a great idea.
Thank you.
Last question? Very cool. So my question is, have you perhaps explored anything related with the tactile perception, the haptic perception, maybe the kinesthetics? Have you ever explored anything related with that?
So not yet, but that's actually something that I always have in the back of my head, because there is something inherently haptic to it, so I'm wondering how you could kind of bring these fields together. So yeah, it's a really cool idea.
Okay, let's thank our speaker.